back, guys. So we will continue our discussion on thermodynamics, and this is part 3. In this video we are going to discuss about thermodynamic processes. Now, non-equilibrium states of a system are difficult to deal with. As you know that a system is said to be in non-equilibrium state if the thermodynamic parameters or variables like pressure, volume, temperature changes with time. So when these variables changes with time, it's really difficult to really understand the system. So as a result, what we do is that we idealize a process in which it stays in equilibrium at every stage of the process. So a process in which the system stays in equilibrium at every stage of the process is called a quasi-static process. Now, in a quasi-static process, the system variables like pressure, volume, temperature changes very slowly and remains in thermal equilibrium with the surrounding. Since the system variables like pressure, volume and temperature changes very slowly, we say that the system stays in equilibrium at every stage. That's only because the pressure, volume and temperature changes very slowly, thus we say that they are in equilibrium. Now, there can be difference between the system variables and the surroundings, and these changes are taken to be very small, that is infinitesimally small. But even though there are small differences between these parameters between the system and the surrounding, the system takes its time and equalizes these things with the surrounding. So I will try to explain the last 2 points with the help of a diagram here. So consider a cylinder here with the air particles inside this, and this black portion again represents the piston. Let P and T be the pressure and temperature of the system respectively, and let the surroundings pressure be P plus delta P and the temperature be T plus delta T. So you can see that the pressure and temperature of the system is different from that of the surrounding by a very small amount, that is delta P and delta T. So if the system takes its own time, that is it takes a very large time, and at last it attains the same pressure and temperature of that of the surrounding, that is P plus delta P and T plus delta T. So the key point you should note that is that a quasi-static process is a process which takes place very slowly, such that it stays in equilibrium with the surrounding at every stage of the process. And this quasi-static process is quite hypothetical, but what we see is that a lot of processes in our surrounding can be approximated to quasi-static processes, and it's easy to deal with the quasi-static processes. So all the processes in the coming slides and which we are going to discuss are assumed to be quasi-static. That is, it is assumed that the system remains in equilibrium at every stage of the process. So, isothermal process. Any thermodynamic process in which the temperature remains constant, we say that the process is isothermal. Now, in the case of ideal gas, we know that PV is equal to nRT, and if the process is isothermal, that is T remains constant, then we get that PV is equal to constant. So, in the case of ideal gas, the thermodynamic process is represented by this equation, that is PV is equal to a constant. Now there is another important point which you should note here, that as you know, P, V and T are the state variables of the system, and this is an equation which connects the state variable. This is also known as equation of the state. Now, work done during an isothermal process. So as you know that W is equal to V1 integral P dV from V1 to V2. Now we know that PV is equal to constant is the expression for the isothermal process in the case of an ideal gas. So if we substitute the value of V from the equation, we get that W is equal to nRT into integral V1 V2 dV by V, and if you do this integration you will get that W is equal to nRT ln V2 by V1. So this is the expression for the isothermal process of an ideal gas. Now, in the case of an ideal gas, as you all know that the internal energy depends only on temperature. So as a result, in an isothermal process where the temperature does not change, the delta U is 0. So uh, the first law of thermodynamics changes to delta Q is equal to W. The equation of the first law of thermodynamics changes to delta Q is equal to W. Now, what all things can we interpret from this equation? Now, this is work done W is equal to nRT ln V2 by V1, which we have already derived. Now, when V2 is greater than V1, that is in this equation, when V2 is greater than V1, this ln V2 by V1 is a positive quantity. As a result, the work done is positive. Now, if V1 is greater than V2, then what happens is that this ln V2 by V1 is a negative quantity and the work done is less than 0. Now, if we use this information in this equation, what we get is that during an isothermal expansion, that is, if a system expands, as you all know that volume increases, so that is V2 is greater than V1, the work done is positive. As a result, delta Q is also positive. So if delta Q is positive, that means that the system has absorbed the heat from the surrounding. So again I am stating the statement. In an isothermal expansion, the system absorbs heat from the surrounding and does work. Now what will be the other way around? So in isothermal compression, that is during compression, as you all know that the volume decreases and V1 is greater than V2, the work done is negative. So if work done is negative, from this equation we get that delta Q is negative. So what does it mean by delta Q is negative? That is, the system has released the energy to the surrounding. Thus we get this statement: during isothermal compression, work is done by the surrounding on the system and heat is released to the surrounding. Now here are different graphs of isothermal process in the case of an ideal gas. So in the case of an ideal gas, as you know that P and V are inversely proportional. So this is the PV graph for an isothermal process. And VT graph, in VT graph the temperature remains constant, so it's a straight line, and in VT graph the temperature remains constant, so again this is a straight line. So these three are three different graphs with three different variables on the x-axis and y-axis, and these graphs represent the isothermal process of an ideal gas. So next we will discuss about isochoric process. So a thermodynamic process in which the volume remains constant, we say that the process is isochoric process. Now in isochoric process, the work done is 0. So as you know that W is equal to P delta V, and in isochoric process there is no change in volume, that is delta V is 0. As a result, the work done is 0. So as you all know that dq is equal to ncv dt plus pdv. We have already derived this equation. So in the case of isochoric process, dv is 0. So the equation changes to dq is equal to ncv dt. So what's the importance of this equation? So if you know the molar specific heat capacity at constant volume of a substance, we can always measure the change in heat energy given the change in temperature, or vice versa. Means that is, if there is a change in heat energy, we can calculate the change in temperature once you know the molar specific heat capacity at constant volume. Now These are three different graphs which represents the isochoric process of an ideal gas. So this is a PV graph, so volume is a constant, so it's a straight line again here. This is a VT graph, volume is constant, so again a straight line. Now, in the case of an ideal gas, you know that P and T are directly proportional. So again, the PT graph is a straight line, but it's not parallel to X or Y axis. And another important thing which you should note that in all these cases, I assume that the temperature is measured in Kelvin. So if the temperature is measured in Kelvin only, then this straight line passes through the origin. If the temperature is not in Kelvin, then this line will not pass this the origin. So this is a point which you should note. So again, I'm repeating, the thermodynamic process is called isochoric if the volume does not change. So now we will discuss about isobaric processes. So a thermodynamic process in which the pressure remains constant, we say that it's a isobaric process. So now we will calculate the work done during an isobaric process. So already you know that W is equal to PdV, integral PdV from V1 to V2. And if you integrate this, that is if you take P outside and integrate dV, you will get W is equal to V2 minus V1. Now, in the case of ideal gas, you know that PdV plus VdP equal to nR dt. This equation we have already derived in our previous video. And in the case of an isobaric process, that is that pressure is constant, dP is 0. So you get PdV is equal to nR dt. And this equation of the work done changes to W is equal to integral nR dt from T1 to T2. So when you integrate this, you get W is equal to nR T2 minus T1. So these are the two equations for the work done during an isobaric process. And these are the three graphs which shows isobaric process in the case of an ideal gas. And as you know, in the case of an ideal gas, V is directly proportional to T, so you get a straight line which passes through the origin. So now we will discuss about adiabatic process. So a process in which there is no exchange of heat between the surrounding and the system, we say that the system undergoes an adiabatic process, and since there is no exchange of heat between the surrounding and the system, delta Q is 0. Now, an adiabatic process is represented by the equation PV P into V raised to gamma equal to constant, where gamma is nothing but the ratio of Cp and Cv, where Cp is the specific molar heat capacity at constant pressure and Cv is the specific molar heat capacity at constant volume. Now, it's important to note that since Cp is greater than Cv, because Cp is equal to Cv plus R, Cp is always greater than Cv, therefore gamma is always greater than 1. Now, how did we get this equation? So, in NCERT you will not find how they got this equation, but I will derive here how we get that P into V raised to gamma equal to constant is the expression for an adiabatic process. We are able to derive this equation mainly because of the two main equations which I have already derived in my previous video. So I hope that you remember these two equations which I have already derived in my previous video, that is dq equal to ncp dt minus vdp and dq equal to ncv dt plus pdv. So these two equations I have already derived in my previous video, and if you haven't seen that, you can go through that and you will see how I derived these two equations. Now, in the case of an adiabatic process, I said that delta Q is 0, so that is the left hand side in both of these equations is 0. So in the case of first equation, we get that Cp dt equal to Vdp, and in the case of second equation, we get that Cv dt equal to minus Vdv. Now, if we divide these two equations, we get this equation, that is Cp by Cv equal to minus Vdp by Pdv. Now, Again, if we make some rearrangement and substituting gamma is equal to Cp by Cv, we get minus gamma into dV by V equal to dP by P. Now we will integrate on both the sides, so we will get minus ln V raised to gamma plus C equal to ln P, where C is a constant. So this constant comes when we do an integration, so that is constant of integration, and we will rewrite this constant in term of another constant, that is K, such that C is equal to ln K. Now then again, if we take this minus ln V raised to gamma to the RH right hand side, we get ln K is equal to ln P plus ln V raised to gamma. So as all of you may be knowing that ln of A into B is nothing but ln A plus ln B. So we get ln K is equal to ln PV raised to gamma. Now we remove this ln, then we get PV raised to gamma equal to K. You may be facing difficulty in understanding the last three lines if you don't know about logarithmic function. So if you go through the logarithmic function, you will understand what I have done in the last three steps. These are just basic of logarithm which I have used here. So in the end, we get PV raised to gamma equal to constant. So this is how we get the equation for the adiabatic process. So that is P into V raised to gamma equal to constant. So now we will derive the expression for the work done in the case of an adiabatic process. So as you all know, W is equal to integral P dV from V1 to V2, and in the case of an adiabatic process, we know that P into V raised to gamma is equal to constant. So if you substitute the pressure from that equation in this equation, you will get W is equal to K into integral dV by V raised to gamma from V1 to V2, where K is the constant. Now if you do this integration, you get W is equal to P to V2 minus P1 V1 by 1 minus gamma. So I have not done the integration completely here, I have just written the final answer. Now in the case of an ideal gas, you all know that PV is equal to nRT, and if you use this equation in this equation, you get W is equal to N into R into T1 minus T2 by gamma minus 1. So here there is an important point which you should note, that since gamma is greater than 1, the denominator is always positive. Now the equation of the first law of thermodynamics reduces to delta U is equal to minus W, because the delta Q is 0, because there is no exchange of heat energy between the surrounding and the system. Now let us try to understand what these two equations means physically, that is W is equal to NR into T1 minus T2 by gamma minus 1 and delta U is equal to minus W. Now if T2 is less than T1, so in this equation if T2 is less than T1, then the numerator is positive, the denominator is already positive, so W is positive. So if W is positive, that is work is done by the system, that's why we get W is positive. And if you substitute that in this equation, since W is positive, you get delta U is delta U as negative. So if delta U is negative, that means internal energy of the system decreases. So what it means that in an adiabatic process, if work is done by the system, then the internal energy of the system decreases. Now if T2 is greater than T1 in this equation, you get the numerator to be negative, the denominator is already positive, so you get W as negative, that is work is done on the system, because W is negative, work is done on the system, and since W is negative, here you get delta U is equal to positive, that is the internal energy of the system increases. So that means that in an adiabatic process, if work is done on the system, then the internal energy of the system increases. Now there is another important thing which you can understand from here, is that if T2 is less than T1, that is the final temperature is less than the initial temperature, then it means that the internal energy of the system decreases, and if the final temperature is greater than the initial temperature, then the internal energy of the system increases. So now we will compare the slope of a PV graph in the case of an isothermal and an adiabatic process. So for an isothermal process, you know that PV is equal to a constant, and if you differentiate this equation with respect to V, we get V dP by dV plus P is equal to 0. So why are we doing that? Because the slope of the PV graph is nothing but dP by dV. So if you take this P to the RHS side and V to the RHS side, you get dP by dV is equal to minus PV. So the slope of an isothermal process in the case of a PV diagram is nothing but minus P by V. Now, in the case of an adiabatic process, P into V raised to gamma is a constant. So again here we divide with respect to V. So we get, not divide with respect to V, we differentiate with respect to V, and we get V gamma dP by dV plus gamma into V gamma minus 1 is equal to 0. Now again if you rearrange, you get dP by dV equal to minus gamma P by V. So this is the slope of the adiabatic process in the PV graph. Now if you compare this, you see that there is a difference in the factor of gamma. In the case of adiabatic process, the slope is greater than that of the isothermal process by a factor of gamma. So how can we represent this in the case of a graph? So here I have drawn a PV graph with pressure on the y-axis and volume on the x-axis. So from these two equations, you can see that the slope of the adiabatic process is greater than the slope of that of the isothermal process. So in this case there are two graphs, that is graph 1 and graph 2. Since graph 2 has a greater slope than graph 1, graph 2 represents the adiabatic process and graph 1 represents the isothermal process. So this is a very important point which you should note, that is the slope of an adiabatic process is greater than the slope of an isothermal process in a PV graph. So now we will discuss about cyclic process. A process in which the system returns to its initial state is called a cyclic process. That is, the system starts from a particular state and returns back to the initial state at the end of the process is called a cyclic process. Now, as you already know that the internal energy of a system is a state function. So in a cyclic process, the system comes back to the initial state. So the change in internal energy of the system is 0. So that is, in a cyclic process, the internal energy of the system, change in internal energy of the system is 0. Now, as the internal change in internal energy is 0, we get delta Q is equal to W from the first law of thermodynamics. That is, the change in heat energy is equal to work done. It can be work done by the system or work done on the system. Now, the cyclic processes are always represented by a closed loop. Now, why is it that so? So let's imagine the process starts from a particular point, it reaches back to its initial point. So it's always a closed loop. So if you take any graph here which is shown, you can see that in all these graphs the system comes back to its initial state. So all these graphs represents a cyclic process. So we will stop our discussion here and we will continue in the next part.